Good afternoon. This is Kathy Ritzman of NPCA, and we'd like to welcome you to today's webinar titled Precast 101. Upon joining the webinar, you will need to choose your audio preference. You're able to listen to the presentation through your computer speakers, or you can join the webinar by phone by dialing the number listed on the screen using the access code provided. We encourage you to have a copy of the presentation that was emailed to you so you can follow along and take notes. We have muted all participants to eliminate background noise since we will be recording this webinar. Also, for attendance purposes, we would like to know how many people at your location are participating with you today. If you could please use the questions section to let us know the names of the individuals in attendance, we'd appreciate it. Most importantly, this is an interactive session, and we encourage you to ask questions. If you do have a question you would like to ask the presenter, please use the question function to type your question or comment. Now I would like to introduce today's presenter, Kayla Hansen, Technical Services Engineer with NPCA. Kayla graduated from Purdue University in 2003 with a BS degree, in 2013 with a BS degree in Civil Engineering and emphasis in structures. She is an engineer in training and serves as staff liaison to the Building Product Committee, Utility Structures Product Committee, and the Stormwater Product Committee. I will now pass the controls over to Kayla to begin the presentation.
Hello, everybody. Thank you so much for joining us. We have a fabulous presentation for you. So if you could make sure you are following along, that would be great. And like Kathy said, if you have any questions, just type them in. Nobody else can see the questions that you ask, but we will answer your questions verbally. So feel free to interrupt at any time and ask whatever you are unsure about. Okay, so a brief overview. We are going to start with the properties of fresh concrete, and we'll move on to the constituent materials, what goes into concrete. Then we will follow up with batching and curing, and we will wrap up with properties of hardened concrete. And before we get into the properties of fresh concrete, I wanted to talk about, really briefly, the 5 basic types that you will see. So the most common one that you'll run into most often is wet cast. The water to cement ratio, which we will discuss in further detail later. But if you want to take notes on this stuff, that might be helpful for you later, so you can differentiate between the different types and their different characteristics. But for wet cast, the water to cement ratio is usually 0.4 or greater. The slump for wet cast is typically 4 to 7 inches. It can be lower or higher, but most often it is in the 4 to 7 inch range. Wet cast needs to be consolidated either with internal vibrators like stingers or external vibrators or form vibrators. Wet cast is typically stripped the very next day, and the compressive strength typically ranges between 3,000 and 6,000 psi, with most mixes achieving strengths between 3,000 and 5,000 psi. Next up is SCC, self-consolidating concrete. It uses the same water to cement ratio typically, but it's more flowable, and that is attained through the use of admixtures. Instead of a slump, we measure its spread, and that typically ranges from 22 to 27 inches. Again, that can be greater or lower, but most often it's in the 22 to 27 inch range. SCC also has less coarse aggregate than wet cast, and a greater quantity of fine materials, in addition to the use of admixtures to achieve that flowability. Dry cast is a unique type of concrete. It usually has a water to cement ratio ranging from 0.3 to 0.38, and this is also called no slump concrete. And if you do your slump test, it's supposed to be 1/4 inch or less. It is made with mechanized equipment instead of your traditional method of pouring or casting. And it's unique in that it can be stripped immediately after casting and consolidation, so it helps you with mass production of pipes or manholes and stuff like that. Next up, this is less common, at least around us, but HPC and UHPC, this is high performance concrete or ultra high performance concrete. For UHPC, the water to cement ratio is significantly lower. It's usually around 0.22, and this can reach strengths between 18,000 psi and 28,000 psi. So when you compare that to the wet cast mix we were talking about that most of you guys probably use, that ranges from 3,000 to 6,000 psi. So this is significantly greater, and you can use this for making really intricate shapes, as you can see in those photos. Structures with lots of void areas and just really unique products like that. So it's not something that you see very often, and it is significantly more expensive too, but we will get into that a little bit later. So back to what the overview that we started with. So first up is the properties of fresh concrete. So fresh concrete is called plastic, which means that it's flowable and it's workable. It doesn't mean hard like plastic. It means plastic in this sense means that it's flowable. So it only stays workable for a short time, and the properties are measured to ensure that the concrete meets the performance specifications for the job. Properties also relate to the producer's interest in placing and finishing the concrete before it's no longer workable. So these are all characteristics that we need to be aware of. So first we're going to discuss the quantitative characteristics. These are things that we can actually measure and give a value to. A good example for explaining the difference between quantitative and qualitative characteristics would be a painting. So quantitative characteristics would be like the dimensions of the painting, like it's 1 foot tall by 1 foot wide, or the painting itself weighs 3 pounds, something like that that we can give a value to. Qualitative characteristics, which we'll discuss in a bit, those are more subjective appearances. So the painting uses red, yellow, and blue paint or something like that. It's not something we can give a numerical value to. So the big ones that you'll be like doing your QC, your tests for and in your plans are air content, unit weight, yield, slump or spread depending on whether or not you use SDC, and the fresh concrete temperature. The air content is used, you need to measure that if you're using air-entrained concrete. If you're not, then that's not a huge factor. But if you do have to measure your air content, that's done either daily or every 150 cubic yards, whichever occurs first. Unit weight needs to be done weekly or every 150 cubic yards. Slump or spread is done at least once a day. And the temperature needs to be monitored when the air or slump are done and when cylinders are made. So that's typically a daily thing as well. Can everybody hear me okay? Someone had reported that they do not have any audio. If you could just use the little question answer function. Okay, the person who wasn't able to hear us, are you able to hear now? Is that the person who asked? Okay, so first up is air content. So this little diagram shows the difference. So on the left here, this volume of concrete is this amount of space that it takes up is the absolute volume, and these little ovals or voids in here are the air voids. And when all of those voids are summed together, when you add up how much space all of those little air bubbles take up, that becomes the space over here. So you can see that even though, like the cylinder that you cast, if it takes up this much space here on the left, really the amount of concrete that's in that cylinder is better represented by the cylinder on the right here. So the amount of air in fresh concrete refers to the volume of air that is contained within it. So that would be this little sum right here. And it's a measure of both the entrapped and the entrained air. So entrapped air is air that ends up in the concrete. You can't avoid it. It's not. You can do things to minimize it, but it happens when you batch and mix your concrete. And it can also occur when you are pouring your concrete, and it can be minimized when you use internal vibrators or form vibrators, stuff like that. Entrained air, that's something that we add on purpose using admixtures, and we'll get into the details of why that's important later. But when we do measure the air content, it's a measure of both entrained and entrapped, so the air that gets in there on purpose and the air that we can't really avoid that's in there no matter what. So when you do these air content tests, there are 3 different ASTMs that you can use, which are listed right there. ASTM C173 is the volumetric method. 138 is used for density, yield, and air content. That's only used in, it's used less often after you find a relationship between air content and density, so that one's not as commonly used. And then 231 is by the pressure method. Okay, next up is unit weight. This is determined by, you have your bucket, it's a known volume, you follow the appropriate procedures according to ASTM C138 for filling the bucket and consolidating everything. And this is used later on when we calculate the yield. And determining the unit weight, the value will depend on the type of concrete we're making, the type of aggregate we're using, if it's a lightweight aggregate or normal weight or heavyweight, how much cement we use, the amount of air, of course, since the air that's in the concrete isn't going to add any weight to it. And this is just used to help us determine whether or not the concrete is within the specified limits. So if our mix design says that the unit weight is supposed to be within this particular range, and we're measuring our unit weight every day when we batch, and it's out of those tolerances, it'll help us identify some issues and hopefully resolve those issues before it becomes costly or negatively affects the product that we're making. So again, that's also done in accordance with C138. Okay, so the yield is the volume of concrete that is actually produced in a batch. So if your mix design uses 27 cubic feet of ingredients, our goal is to actually get 27 cubic feet of concrete out. 27 cubic feet is equal to 1 cubic yard, so that conversion might be useful to know. And the reason we do yield calculations is to help control the variations between the batches. So if if we're expecting to get 27 cubic feet of concrete from these ingredients and we get more than that or less than that, then it gives us an idea of that maybe something needs to be calibrated because it's out of whack or something like that. It helps us ensure that our product is going to be consistent and also helps keep track of like wasteful batching or something like that. So if we're putting in too much cement or something like that, because that's a very expensive ingredient. So this just helps reduce or eliminate the variations between batches. So this, let's see, I think this slide in your presentation appears a little bit later on, but I just included it again here to use as a little bit of an example. So if we have down here, so we'll do a little yield calculation quickly. So the yield is equal to the weight of all the materials, which is right here. That's 3,950 pounds. And please, I promise I don't normally write this horribly, but I'm using the little trackpad, not a pen. So that says 3,950. And then we divide it by 27. Oops, sorry. We divide it by the density of the concrete. And that can range from 145 pounds per cubic foot or up to 150. So let's just say here that our density is.
Is everybody able to hear us? We've received a couple of notices that we don't have audio. Can you let us know if there's any sound?
No, we have no visual. It's not advanced. Okay.
We're good. Okay.
All right. So the slide has not advanced for a while, so you're just writing on it.
Yeah, you should see a table with different cement or different concrete ingredients like cement, fly ash, water, and then some different numerical values. And I'm just writing on it right now.
Okay.
Rather horribly.
But we're good.
We're going to do a quick yield calculation. So this slide I don't think appears in your presentation at this point. It appears later on, but I just included it again just so we can do a quick example. So we're going to do a yield calculation. Down here I have written Y yield equals 3,950 pounds, which is the weight of all the ingredients that we put into this batch. And we're expecting to get out 27 cubic feet of concrete, which is equal to 1 cubic yard. So we're going to say that the density, we did our unit weight test, and we came up with a value of 147 pounds per cubic foot. That says FT cubed. Okay, so we divide our total weight of the ingredients by the density. So divide this by 147. Claude, do you have a calculator?
I can. Oh, sure. Or somebody else could.
Or if anybody else has a calculator handy or has their phone handy, you can tell me what value you get. So we'd like to see, well, I guess first just tell me what value you get, please. So 3,950 divided by 147. Okay, one person says 26.83. I think that's what that says. Okay. Okay, everything there looks good. Okay, so we got a, oopsies. So we ended up with 26.83 cubic feet of concrete. So we were supposed to get 27. That's what we were hoping for. So our yield is just a little bit low. And if you want to find the ratio that actually is, you can just do the 26.83 divided by 27, and you'll get a decimal. That's around 99.5%. So we're pretty darn close. And I can go over that again later, or write it on the slides nicely later, and then redistribute that out to you guys if you'd like. Does anybody have questions on what we've discussed so far? If you do, just shout them out or write them in the question-answer function. Okay, so moving on, these yield calculations are outlined in ASTM C-138. You've seen that that one listed a couple times before. It has a lot of very useful information in it. But again, the yield calculations are done to help control the variations between batches and make sure everything's staying in check there. So slump and spread. Why do we do a slump test? If you could please each reply and tell me why we do them. What's the purpose of it? To measure flow. Okay, why do we do a slump test or a spread test? What is the purpose of doing these tests?
And not,
okay.
and because it's required, it's not an answer.
So one person wrote consistency, one to measure flow, workability, flowability, workability, check consistency. So yes, that's really good actually. Slump tests are done to measure the consistency. Two different types of consistency actually. The consistency of the concrete itself, the flowability of the concrete, the ability for fresh concrete to flow, and the consistency between batches. It is not a measure of how much water is put in the mix. It's not a measure of the water to cement ratio, and it's not an indicator of the concrete strength. So those are really common misconceptions. So the reason we do a slump test or a spread test is to make sure that our concrete is staying consistent between batches, and to ensure that the concrete or the consistency of the concrete we just produced is appropriate. So again, just to reiterate, it's not a measure of the quality, it's not a measure of how much water we put in, and it's not an indicator of what the water to cement ratio might be. So if you're doing a slump test, that's done in accordance with C-143, and if you're doing a spread test, that's C-1611. Okay, temperature tests. This seems like a really minor thing to test for, and it's probably, hopefully, the easiest one to do. But it's actually extremely important, because if the concrete is too cold, for example, if it freezes before it reaches only 500 psi, then you have to toss it out. You have to discard it. It greatly affects the concrete's ability to develop strength, and it stunts the crystal growth that we'll talk about later. So it really, really impacts the concrete in a negative way if it's too close or if it's too cold. And again, if it's too hot, that also has a detrimental effect. So the reason we test for temperature is to ensure that it's within the appropriate limits. So if in cold, really cold conditions, and a lot of times your plant-specific QC manual should have procedures written in it for hot and cold weather concreting. And include the appropriate precautions to take when you're experiencing that sort of situation. So in hot conditions, the concrete at the time of placing, it's not supposed to exceed 90 degrees Fahrenheit, and in cold conditions, it is not to drop below 45 degrees Fahrenheit. So the temperature range that you want to keep your concrete within is 45 degrees Fahrenheit up to 90 degrees Fahrenheit. And of course, there's an ASTM for this test as well, and it is C1064. So next up are the qualitative characteristics that we wanted to talk about. So before we were just discussing the numerical value too, and now we are going to discuss the more appearance-based characteristics or observances that we could describe. So finishability Okay, so finishability is it's just how easily we can manipulate the surface once it's placed and manipulate it to finish it and give it that smooth or whatever sort of texture we're going for. Sometimes water is added to help achieve a smoother finish, and this practice can be okay as long as it's what is specified. Sometimes you'll just have water added when it's not called for, and this water just most of the time just sits on top of the concrete surface and pools up there, and adding that extra water changes the water to cement ratio and makes it very, very watered down, and that affects the strength of the concrete. It makes it a lot weaker, and it can just, sometimes if you rub your finger across it, it'll leave this dirty, like cementy stuff on your finger. So it's not a good idea. So water added before the concrete sets, that will alter the structure. So again, if it's specified, then make sure you're following those directions. But if it's not something that's called for and your mix isn't the appropriate consistency that you were looking for, then that's an indicator that something else may have gone wrong in the batching process.
Now, Kayla, we got a question here from one of the attendees,
Okay.
and it says, what about water curing? Does that increase the water to cement ratio?
Okay, that is something that we'll get to later on, but no, it does not. So sorry, no. If you're using moist curing methods, that is not going to affect the water to cement ratio. That's not getting inside the concrete. It's not affecting the matrix. It's not doing anything like that. So it's only helping the concrete become stronger, and we'll get into that a little bit later on. And again, if you have any other questions, just feel free to ask them, and Claude or Kathy will point them out to me, and we'll stop and answer them. Okay, segregation. So this is something else that we notice at times. This is when the coarse aggregate tends to settle to the bottom. It separates from the paste and the mortar. And as you can see here, this is just mortar up here. This is just the cement and the water and sand. And down here, we just have a very high concentration of the coarse aggregate. So this non-uniformity also affects the compressive strength, and it's going to affect the performance of your product. And we will, so some of the ways that you can avoid this is placing the concrete in an appropriate way, so you're not dropping it from 20 feet in the air into the form. that would cause the coarse aggregates to settle. Also, you can use viscosity modifying admixtures, which help suspend all of the materials, including the heavier ones like coarse aggregate, evenly throughout it, so that there aren't any issues with settling. So when you do have segregation, or also over consolidating, that can do it too. But when you do have segregation, it can also lead to, in addition to affecting the concrete strength, it can also lead to just rock pockets and honeycombing. Okay, bleeding. This is something that I think is pretty common. How many, just give us a yes or a no, how many of you guys see this in your plant? When there's water pooling up here, or it looks really, really wet on the surface? Occasionally, sometimes. So on some of the pre-assessments that I've gone on, this is one of the big, this is something that we see pretty often. This could be because the water to cement ratio is just too high. The water, there's no more cement left to react with, and it tends to migrate to the top, and it just pools up there. And again, this is what I was just talking about before. When this happens, it changes the water to cement ratio on the surface of the concrete and makes it significantly weaker, which can result in something like this bottom picture down here happening. And again, this can also be worsened by segregation when the heavier ingredients settle to the bottom or settle down, causing the water to migrate to the top. And one other note about this, bleed water, it's not a bad thing. It happens, it's common, it just needs to be controlled and not worked back in to the concrete while you're finishing the surface. Okay, next up, constituent materials. So this snazzy little tree diagram, that's what I'll call it, is a breakdown of what goes into concrete. So the bare minimum, these are just the basics. So concrete is made up of binder and filler, binder being the paste and filler being the aggregates, the coarse and the fine aggregates. So binder, or the paste, consists of just water and cement. So at the very minimum, these are the 4 things that you'll have in your mix. And just a little clarification, paste is the water and the cement. Mortar is different than concrete. It's not mortar is not paste, mortar is not concrete. Mortar is paste and fine aggregate. So mortar is water, cement, and fine aggregate such as sand. Okay, so again, the 3 or 4 things on top that are in purple are the basic things that you'll find in any mix, and we'll discuss those first. And then we'll go on to the admixtures, air, and other cementitious materials that aren't necessarily going to appear every time. Oops. So I'm sure you've all seen this before. Apparently this is what goes into chicken nuggets at McDonald's. Hopefully,
Oh.
I don't know if you, sorry if I ruined your appetite, but it's pretty gross. Anyway, this is just a reminder that filler is cheaper, which leads me into aggregates. Aggregates are the filler. Aggregates are cheaper than cement. Does anybody, could you let me know who you guys think this little handsome character is? I don't know if you guys recognize him.
That's me from college.
Claude in college, yep. He-Man, yeah. Okay, so He-Man was known for his superhuman strength. So I put his very attractive wig on a pile of coarse aggregates because they are the inert filler that, besides cement, gives concrete its strength. Okay, so there we go. So when I say inert, that just means that they're not supposed to be reactive. They're not really supposed to do anything except for sit there and be strong. We don't want them to have we don't want them to have dirt on them or excessive amounts of chlorides or anything like that. We just want them to sit there and be strong. And they are significantly cheaper. They are the fillers, so they're cheaper than cement. But they do occupy the majority of the concrete volume. So although they are cheaper, their importance cannot be overemphasized. So normal weight aggregates are the ones that we see most often. And they're all pictured here. So on the left we have crushed stone. In the center we have pea gravel. And on the right we have sand. So normal weight aggregates come in the form of coarse and fine. So coarse being your crushed stone here and fine being the sand. And these are just some measurements that they typically fall into. Lightweight aggregates, which are shown here in the top right in the hands, typically, I guess the ones that are most common are expanded clay or expanded shale. Pumice is another lightweight aggregate, but I don't know if I've ever heard of a situation where that would be used. It's really porous. Typically, lightweight aggregates aren't used for structural products because they're not nearly as strong as normal weight or heavyweight aggregates. Heavyweight aggregates, on the other hand, they work really well in radiation shielding, and Claude also shared an example of counterweights. They're like in a washer to keep it from, I don't know, sometimes you'll hear it like banging around. Something's not quite right. So anyway, heavyweight aggregates can be used for making concrete that needs to be very dense and heavier. So lightweight aggregates are typically between 30 and 40 pounds per cubic foot. Normal weight aggregates upwards of 50 pounds per cubic foot, and heavyweight aggregates can be up to 110 pounds per cubic foot. So there's a huge variation there. Okay. Another cheaper ingredient that goes into our concrete is water. And again, this is another very important factor. So we require that you use either a municipal water supply, so we know that there aren't any little critters or impurities floating around in it. Otherwise, if you use well water, that's okay too. We just make sure that we get an annual potability test done to make sure that there aren't too many impurities or too many chlorides or too many of any bad things that would negatively affect the any of the chemical reactions or the long-term strength of the hardened concrete. Additionally, the water in our water to cement ratio doesn't just come from the water that's batched into the mix. It can also come from the aggregates. If it rained overnight, your pile of wet aggregates, that water is going to affect the water to cement ratio, and that will be used. That will alter everything, and that's why we have to do moisture content tests. Additionally, if it's really hot out, your aggregates, they have microscopic little pores on them. They're porous. They can have water inside them. They can have water on the surface. And that's something that we'll get into, I guess, in PQS in more detail. It's kind of interesting, actually. But if it's really dry, those aggregates, when you put them into the mix, they can actually absorb some of your mixed water and alter your water to cement ratio and drop it. And that's something else that we have to account for. So water, we'll get into water to cement ratio in just a minute, but it's another very important factor in determining the long-term strength. Obviously, it affects the workability and durability and porosity of your concrete as well. So reducing water quantity can lead to an increase in strength, and increasing, sorry, I don't know if I said that backwards. Reducing the water quantity can lead to an increase in strength, and increasing the water quantity can decrease your strength. So, I don't know about you guys, but I hear this all the time. I actually just read a CNN article about this lady who crashed into a cement barrier on the highway, and this is what I thought of, this bottom right picture. If you're crashing into a cement barrier, you're just going to have a hot mess and your car's going to be nasty. You're not going to, nothing's going to happen. It's just going to be a cloud of dust. So concrete and cement, there is a huge difference. Cement is an ingredient that goes in concrete. It is a very fine powdery substance. Concrete is the hardened product that you get when you mix water, cement, and aggregates. So, huge difference there. Okay, Portland cement. It is a synthetic, typically gray powder. You can have white cement if you're doing architectural products where the aesthetics are more important. But it is made by firing limestone powder and clay in a kiln, I think in excess of 2,000 degrees, something really crazy. And after it comes out of the kiln, you grind it together with gypsum. Gypsum actually slows down the process, because if it didn't have the gypsum in it, it would just set immediately as soon as water was added. So that's why we add the gypsum. So we have limestone, clay, and gypsum all ground together and make this fine powder. And cement is called a hydraulic material because it is very reactive with water. And for anyone who's interested, it got its name. Portland's not like a brand or anything like that. It came, someone decided that it looked like the limestone that they saw in England, which was off the island of Portland. Yeah, something like that. Yeah. Very important fact. This is another slide that you guys don't have. I just added it this morning to help give you a more visual, prettier picture of it. So here, this is limestone. I'm just going to call it, there we go. There's a difference between lime and limestone, but my writing is horrible, so I'm just going to call it lime. And please just make note that that is limestone. Next up in the center is clay, and then this white powder on the right, that is gypsum. So those three combined together, we get Portland cement. And this is one other slide. Promise there aren't any more surprises like this. One other slide that I added. But if you could please fill these in. The four main oxides that we find in cement are lime, which is CaO. So this top line should say lime, not limestone, but lime. And this comes from the limestone. Next up is iron. And that comes from the clay that is in the cement. Then we have silica, also comes from the clay. I know this is a painful process watching me write. And last is alumina. And that also comes from the clay. That says alumina. Sorry. Okay, so the 5 main types of cement, there are different variations within these types, but they're very detailed and not particularly important right now. What's most important is that we identify what these types are used for. So the one that you'll see most often is type 1. Can you tell me, does anybody use something other than type 1? Does anyone use type 2, 3, 4, 5? Or does everybody use type 1? Is everyone asleep already? Type 1, 2, okay. Okay, one person's awake. So type 1 is used, it's just normal. It's just general purpose cement. So if we're not designing this product for any particular special use, it doesn't require any really snazzy properties, then we're just going to use type 1. Type 2, that's used, it's our moderate sulfate levels. So sulfates come from, sulfates come from like salt, so like de-icing salt, stuff like that. Rapid setting concrete, that's type 3. They're used in rapid, when you're trying to make rapid setting concrete, so if temperature is a concern or something like that, the ambient temperature. Type 4 is used when temperature rise is a concern. So when cement and water come together, that chemical reaction is called hydration, and it's an exothermic reaction, which means that it gives off heat. So if you're pouring a gigantic mass of concrete, like a bridge pier or just something huge, think like Hoover Dam, that's going to create an enormous amount of heat. And too much heat, like we said earlier, we want to keep our concrete lower than 90 degrees. Too much heat can negatively affect the long-term strength of our concrete. So using this type 4 cement, it has more gypsum in it, and it slows down the reaction to prevent the heat from rising too quickly. And this is used most often when you're doing mass pours, really huge things. And type 5, that's used for severe sulfate exposure. So if you're doing something that will be exposed to like seawater or something like that, where it's constantly having chloride attack it, this will help out with that. And I think we had a question. Could you read that, Claude?
Oh, I think somebody was saying there are also some cementitious blends out there. So, and what the person's talking about, you can actually get blends. You can get a type 2 AE, for example, which is type 2 with air entraining in it. So you actually get cement with air entraining in it. You can get type 1, 2. You can get a type 1 with fly ash. You can get fly ash or slag blends. So it's not, it's not like it used to be where you just got cement. You can get all kinds of blends now for whatever you need. And then somebody said, okay, that's a logistical question. You're good to go.
Okay. Okay, so as we were just saying, cement and water, they begin reacting as soon as they come in contact. Hydration is what this chemical reaction is called. It's the reaction between cement particles and water. And this reaction gives off heat. You know, when you're in the plant, you can feel the next, shortly after it's setting, it's already giving off heat. It's warm or hot to the touch. Okay, so the main products of a hydration reaction are CSH and CH. CSH is the good stuff. It's stable. It's the main product of the reaction, and it's the main source of strength in the concrete matrix. And this microscopic little thing down here, this is what CSH looks like. Now, CH, that is another product of this hydration reaction. And it's not produced in as great of quantities, but it's not stable, and it's not something that we like to see as a result of our hydration reaction. So as the cement particles react with water, they develop these crystals, and these crystals become interconnected and develop the concrete matrix. And as this hydration continues, this matrix becomes stronger and more dense. So we'll take a more detailed look at that. So figure 1 is immediately upon the addition of water. So that's just cement and water right before they start to react. So figure 2 shows how reaction has just begun. This dark outline on the these little cement particles, these are the products of the hydration reaction. This is the crystal growth just beginning. And as we progress, the hydration is continuing. More hydration products are forming. It's getting thicker. They're becoming interconnected. We reach initial set in the middle of this stage 3 area. Things are getting less workable. And when we reach stage 4, when we have excessive hydration products forming, hardening is occurring. And this whole time, the matrix is becoming more dense and more solid and firm and hardening. Okay, and initial set is when, so stages 1 and 2, we call them dormant because the concrete is still plastic, and remember plastic means that it's workable, it's wet, it's fresh, and it can still be handled in place. So setting is starting to occur in stage 3, and hardening is occurring in stage 4. So water to cement ratio, this is what you've heard me yapping about since we first started. What is the water to cement ratio? It is the weight of water divided by the weight of cement or cementitious, all the cementitious materials that go into your concrete mix. So if you are putting in 226 pounds of water and 564 pounds of cement, when you find the, what is that, the quotient, I believe that's called. When you find the quotient, you'll get 0.40. So that is your water to cement ratio. So a water to cement ratio between 0.40 and 0.45 is what's really required for proper cement hydration. If you have a water to cement ratio greater than that, so 0.6, 0.7, something like crazy like that, when you have just excessive amounts of water, that water remains in the concrete matrix. There's no more cement left to hydrate with that water. All the cement has reacted. There's nothing left. So that water stays in the matrix, and eventually it'll evaporate and just leave these void spaces. And void spaces, just air has no strength at all to it. So that really detrimentally affects the long-term strength of your concrete. So that's why water to cement ratio is one of the millions of reasons why water to cement ratio is so important. So when if there's excess water, eventually it'll evaporate. It won't react. There won't be enough cement there to react. So that water, when it evaporates, it'll leave these air pockets, and it makes the concrete much more porous, and it acts like a sponge, and it just absorbs nasty things, chlorides, whatever else. So this graph is pretty interesting. So the line I want you to pay attention to is this top line that I'm kind of outlining in red here. So this is the 28-day strength. When we talk about concrete, we're typically referring to the 28-day strength or the design strength. So if we have down here on this going horizontally, we have the water to cement ratio. Here we have 0.6 in the bottom right corner. So if we follow this up here, this gives us, oh, and again, sorry, this is an SI unit, so I couldn't find as good of a graph that gave you as good of a representation in English units, so I've made the conversions for you. But if we have a water to cement ratio of 0.6, our 28-day strength will be around 18 megapascals, which equates to about 2,600 psi. So a water to cement ratio of 0.6 will give us, in this particular, with this certain mix, it'll give us a compressive strength of 2,600 psi. So in comparison, a water to cement ratio of 0.5, that will give us a compressive strength of about 25 megapascals, which is 3,600 PSI. So already there's 1,000 PSI difference in just a 0.1 variation in your water to cement ratio. So if we go all the way down to 0.4, that will give us a compressive strength of about 33 megapascals, which is 4,800 PSI. So you might not see, it might not seem like a big deal to add 10 more gallons of water, but I did a little calculation here. So if we have 600 pounds of cement and 360 pounds of water in our mix, that'll give us a water to cement ratio of 0.6. So if we have 360 pounds of water and 600 pounds of cement, that'll give us 0.6. So if we lower that and go down to 240 pounds of water and the same amount of cement, we're still going to use 600 pounds of cement, but we're lowering this by 120 pounds of water, that will give us a water to cement ratio of 0.4. So up here we get 0.6, and down here we'll get 0.4. And water at about 8.3 pounds per gallon, this ends up being a difference of only 14 gallons of water. So a 14-gallon difference in your water can change your water to cement ratio from 0.6 to 0.4, and it can drop your strength from 4,800 down to 2,600 PSI. And that's only 14 gallons of water. So you can see how significant of an impact the amount of water has on your concrete strength and your product's performance. Any questions on what we just talked about? Okay, I think we're all good there. Oops, sorry, one more slide that I added I think you guys don't have. This is just another example, just for your own reference, of water to cement ratio of concretes and the different compressive strengths that you'll get. Now, air-entrained concrete, which we'll get into in just a minute, you can see that why do we add air to our concrete? Look, the air-entrained concrete has a, oops, this was not the right slide. Anyway, excessive amounts of air will decrease the long-term strength of your concrete, but we'll get into that in a minute as to why we do add air entrainment to our mixes. And there's one more slide. It shows up really dark on my screen. Hopefully you guys can see it. If not, just let me know. But again, we're just showing here how using excessive amounts of water, you can see down here as the water to cement ratio increases, the strength just dramatically drops. And again, the air-entrained concrete down here, this green line, shows that it doesn't give you as high of strength because it does have those extra air voids in there, and air, just blank void spaces, they don't have compressive strength. They don't offer any strength in that sense to the concrete. So we talked about the 3 bullet points, or those 4 actually, constituent materials. Those are the basics that your mix will have. So next we will get into the optional things that we can add. So first of all, well, also air isn't really optional, but entrapped air, that's something that you're going to get no matter what. Entrained air is something that is optional. And did we have a question? What is the perfect water to cement ratio? That, there really isn't an answer to that. It depends on your mix and what's all going into it. But the ratio that will allow the concrete, or the cement to fully hydrate with the amount of water was 0.42?
Yeah, there's a couple of models out there. Power's model showed that 0.42 was the water-cement ratio in which there was no cement, no water left over in the experiment they did. But then there's another number out there that's more like 0.26 or 0.28 being the number at which complete hydration is done. So as far as perfect water-to-cement ratio, if you're referring to what's the water-to-cement ratio at which there is no cement, nor is there any water left over, you know, I think it's closer to the 0.2 something, 0.26. But the perfect water-cement ratio would not be that in terms of workability. It'd be impossible to cast it and get it around stuff. So I guess the question to the perfect water-cement ratio is just enough water to hydrate the cement and just enough water to achieve the workability you need to get full envelopment of the reinforcing aggregate, so whatever that may be.
And why do we exceed that number? That magic number that we were just talking about, is that what you were referring to?
Yeah, why would you ever exceed a perfect water-cement ratio, or why would, you know, and I think we just answered that. Water convenience, you know, water added to, in order to work the concrete, in order to get it around reinforcing, etc.
Yeah, good questions.
Yeah, good question.
Okay, so moving on to additional materials that make up concrete. So these are ranges, just general ranges for wet cast, but these just show the different volumes that take up. So aggregates, both coarse and fine combined, can take up to 3/4 of the volume of concrete. Cementitious materials, so cement, fly ash, silica fume, stuff like that, between 7 and 15. Water can be a pretty hefty portion, and air, although it's not something that we always, you don't just like blow bubbles of air in there, but it's not something that you put in there all the time. But entrapped air, that just happens when we're mixing the concrete, that ends up being in there too. So that's just a breakdown of the volumes. Okay, chemical admixtures. How many of you guys use, or what kinds of admixtures do you guys use at your plant? Could you let me know? Do you guys use water reducers, set accelerators, air entrainment? So we have one group that uses admixtures. Does anyone? Okay, maybe not. Water reducers, air entrainers, okay. Those seem to be the most common. Plasticizer, water reducer. Yeah.
Same thing.
Yeah. Viscosity modifying admixture. Air, okay. So this is just a brief list. The list of all the different admixtures that exist is pretty excessive. So I just picked the ones that I thought were the most prevalent that you would run into most often. So water reducers, set accelerators, retarders, corrosion inhibitors, shrinkage reducers, VMAs, viscosity modifying admixtures, and air entrainers. So why do we use them? They're expensive, so what's the point? You can decrease the water content, so you can lower the water to cement ratio while still achieving a workable mix. So as Claude just said, why do we exceed that perfect, you know, quote unquote, perfect water to cement ratio? Why do we exceed it? We exceed it because otherwise it's a pain in the behind to place your concrete. So this is one way that you can achieve a more workable, flowable mix without increasing your water to cement ratio to some ridiculous number and having really weak concrete. So also entrain air, reduce the unit weight, try to prevent segregation, improve your workability and strength. So first up, water reducers. So there are normal, mid-range, high-range, which you might recognize as super plasticizers. These, again, are used to reduce the amount of water that is needed in your mix to make it workable, so you can have a lower water to cement ratio while still being able to place your concrete, get it around heavy congestion like rebar or something like that. Accelerators and retarders. So these, I think, are most often used when ambient temperature weather plays a role. So accelerators will increase the rate that the cement hydration reaction occurs at. So here you can see this little graph down here. I thought it gave a really good example of how it actually, the comparison between what happens with the reaction when you use an accelerator and when you don't. So hours elapsed after mixing are down in the bottom, and the temperature that the concrete is reaching, you can see after maybe 28 hours, it's already increasing dramatically when you use an accelerator. So the reaction, the reason the temperature is increasing is because that hydration reaction has already begun. It's reacting at a much quicker rate, or the reaction starts much earlier. So the concrete will start developing strength at an earlier time. And retarders work in the exact opposite way. Corrosion inhibitors. So if salts, chlorides, stuff like that are something that your concrete is going to be in contact with, or even if you're using rebar and you want to, I believe that would affect the pH of the concrete, because that would help develop that protective barrier film around the rebar.
Yeah, it helps protect that passivation layer around the steel.
Okay. Shrinkage reducers, you don't have to call yourselves out, but sometimes you'll see these spider-like cracks in the unformed surfaces of your product. Those are typically from, they're called plastic shrinkage cracks. So the concrete is, the water in the concrete is evaporating at a rate faster than the hydration reaction is occurring. So it causes, the evaporation of the water is causing tensile stresses within the concrete, and that causes it to crack. So shrinkage reducers can help with the drying shrinkage. So viscosity modifying admixtures, as we talked about before, segregation, here's another a better photo of it. If something is more viscous, it's thicker. Like down here at this picture, there's syrup and water. More viscous, water is less viscous, the syrup is more viscous. So if we are modifying the viscosity of our concrete, we're going to make it thicker and more, I don't want to say goopy, but just a thicker consistency, and that helps suspend the aggregates in the mix so that they don't end up that their weight doesn't just cause them to sink down to the bottom like this, because again, that really detrimentally affects your long-term strength. So air, this is what we've been talking about for the past few minutes in those couple graphs. So entrapped air, those are the big bubbles that you see, like bug holes when you strip everything, and there's these goofy-looking oblong void spaces on the surfaces of your product. Those are entrapped air bubbles. They create large voids, well, large as in 1 millimeter or larger, but typically they're maybe like half an inch, quarter inch, so they can get pretty big. So they're irregular in shape. That's another indicator of what those are caused from. But entrained air, this is something that we've put in on purpose. There are air entraining admixtures which cause microscopic, teeny tiny air bubbles to occur in the concrete, and they're really, really small, so 1/100th of a millimeter in diameter at times. And these are not irregular in shape. These are spherical, and they're not interconnected, unlike entrapped air. So entrained air is a positive thing. It's something we put in on purpose. They're really small air bubbles, and they're spherical in shape and they're not interconnected, so they're likely not going to have a detrimental effect on the permeability of the concrete. So why do we put this entrained air in there? So if your concrete is exposed to freeze-thaw cycles, entrained air is something that you should be using. It helps work as kind of a buffer the same way bubble wrap works when you mail stuff that you don't want to break. It works as a cushion. It gives the concrete, or it gives the water in the concrete a place to expand when it freezes. And this diagram from one of Claude's articles shows how it works. So as the temperatures drop, as water freezes, it expands. That extra space needs to come from somewhere. So as it expands, it takes these little air-entrained little bubbles, these void spaces, and it can fill up those spaces instead of trying to make room in the concrete. So if you're not using air entrainment, that water, when it freezes, it's still expanding, but it doesn't have anywhere to go. So what it does is it pushes out, it puts pressure on the concrete around it, and it can cause cracking. So if you have multiple freeze-thaw cycles, it's just going to constantly put pressure and contract, pressure and contract, and eventually you're going to end up with some really nasty cracks. So a great reason for using air entrainment is to help with freeze-thaw cycles and the expansion that occurs. And I think we have another question. Claude, could you read those, please?
Oh, sure. Yeah, it just says, can air entraining can also be added to, some people use it for workability. They actually don't even use it for freeze-thaw. This particular person's using it, but it's not for freeze-thaw. It's actually for workability. So it kind of acts like ball bearings, so it'll aid your workability, and it'll actually enable you to use less water. So that's another good reason to use it. However, you have to be cognizant that for every 5% or so by volume of, or I'm sorry, for every 1% by volume of air entraining that you use, the rule of thumb is you lose 5% strength. So using less water is good, but you got to balance that out with the loss of strength that you do get when you use air entraining. So that's all it said of the statement.
Thank you, Claude. Okay, so examples of both. On the right here, we have entrapped air. These are large, irregular bubbles. You can see there's a pen in this bottom right picture for scale, so you can see how big those are. In this picture on the left, the entrained air, just to show you how small these are, you can see in this one goldish colored aggregate, there's a little bar on there that says 1 millimeter, which is about the size of this squiggly red line that's supposed to be straight. So that just shows you how small all these little black void spaces are all entrained air bubbles. So that just shows you how small they are. And in comparison, these bubbles over here are significantly larger. Next up, supplementary cementitious materials, which you may heard referred to as SCMs. Does anybody, can you let me know what kind of SCMs you guys use? Do you use fly ash or silica fume or slag or nothing? Do you just use cement? Fly ash, we have one. Fly ash again. Slag. Okay. So SCMs are used to help enhance the properties of straight cement. Okay. SCMs are used to help enhance the properties of concrete, and they can take up to about 20% of the volume of a concrete mix. And like cement, they can be one of the most expensive components of your mix. So again, that's why calculating the yield and doing your compressive strength cylinders gives you a really good idea of what's actually going into your mix. If your cylinders suddenly are just ridiculously strong just out of nowhere, it might give you an indication of something that's going on in your mix, and that can help cut down on costs if you're unnecessarily putting in all this extra cement or all this extra fly ash or something like that. But anyway, so some of the most common ones are fly ash, slag, silica fume, calcium clay, and shale. Those are most commonly used. Oh, and there's one more question?
Yeah, somebody asked, the entrapped air kind of looks like bug holes. Are they the same thing? I think it's a matter of scale. The picture with the entrapped or with the entrained air might be magnified quite a bit. So
right. For scale here, if we're looking on the left, the entrained air, this red line that I'm drawing right here, this is 1 millimeter. So it shows you that all these little entrained air bubbles are 1/4 of a millimeter and significantly smaller, like 1/100th of a millimeter, where these entrapped air voids on the right, you can see that these are significantly larger. There's a pen here, which is, I don't know how thick that is, maybe like 3/8 of an inch or something like that, or less, sorry, like 1/4 of an inch. But so these are significantly bigger. These are not the same scale at all. So this gives you an idea. These are larger than the width of a pen, where these entrained air voids are less than 1/2 millimeter in diameter. Does that clear it up a little bit? And again, entrained air comes from using air entraining admixtures, while entrapped air it's just a byproduct of mixing your concrete or improper consolidation, that sort of thing. And if it's unclear, just let me know and we can talk about that later. So back to the SCM, fly ash can be used to reduce the heat of hydration and improve durability. Slag improves strength over time, and silica fume is extremely fine, and that helps include strength and durability and reduces permeability, I believe, too. Okay, reinforcement. The most common one you'll see is just traditional rebar up here in the top right. There's also epoxy-coated rebar down here, bottom left, the greenish color. And there's also fiber reinforcement, just to name a few. There's steel fibers or all kinds of different materials. Okay, a couple slides that I just added that I thought would be helpful in explaining some rebar facts that are kind of cool. So the numbers, so if you use like a number 6 bar, what the heck does a number 6 mean? It doesn't tell you how strong it is. It doesn't tell you how long it is. It doesn't tell you anything about it except for the diameter. So if you have that little red circle, so that's the end of your bar. The diameter is just straight across, any which way, straight across, cuts through the center. That's your diameter. So a number 6 bar means that it's 3/4 of an inch in diameter. So how do these two numbers relate? Well, the bar size, if you divide it by 8, so it's that many 1/8 of an inch in diameter. So a number 6 bar is 6/8 of an inch in diameter, which is 3/4. A number 5 bar is 5/8 in diameter. A number 4 bar is 4/8 or 1/2 an inch in diameter. So, and the bar size relates to the diameter, and the diameter helps you figure out the area of steel. So all of this space here, the area, which is important for figuring out the how the concrete will react if it's reinforced under tension and compression. So again, the bar size just relates to the diameter. If it's a number 7 bar, it's 7/8 of an inch. Number 8 is 8/8 of an inch, or 8/8 is 1, so it's 1 inch in diameter. So kind of cool little fun fact. Okay, on to batching and curing. Very, very important. So, first off, it's important to note that, does anybody here, do you batch by volume or by weight? Can you let me know? Okay. Okay, so everybody has said by weight, and that's excellent because not that there's anything wrong with batching by volume, but batching by weight is more accurate. So just like, I don't know if this will, I don't know how many guys we have, how many bakers we have with us today, but in baking or cooking, doing everything by weight is also more accurate because you can, like if you're baking bread or something and it calls like banana bread and it says that you need 1 cup of packed brown sugar. Well, I can take the 1 cup measuring cup and just scoop it, and it can just, you know, it can be full, but I can also scoop it again, pack it down, scoop some more on top, shove it all in there, and you can get like, I don't know, like a pound of brown sugar in a 1 cup measuring cup, or you can only have like 8 ounces of brown sugar in the 1 cup measuring cup. And that's using measuring cups is by volume. So if you're batching by weight, a pound of one ingredient is a pound of one ingredient is a pound of one ingredient. It doesn't matter. You know, if you're batching by weight, it's going to be a lot more accurate, and you're going to have, hopefully, more consistent concrete from one batch to the next. Okay, so according to our QC manual, whatever your concrete mix is, you're going to have different specifications. So if your mix calls for 100 pounds of cement, it needs to be within plus or minus 1% of that design weight. So your design says it needs 100 pounds of cement. You can have 1 pound less or 1 pound more. So you can have 99 pounds or 101 pounds, and you'll still be good to go. If you're at 102 pounds, that's no good. So having these tolerances helps keep your concrete consistent from one mix to the next. It helps keep the performance consistent, so we're not getting some super weak concrete, or we're not having all this extra cement in our concrete, all this expensive extra cement for no reason. That's just unnecessarily there. It's making it, you know, 20 times as strong as it needs to be, and it's all this extra money that we're putting into it for no reason. So tolerances are very important, and that's another reason why we require calibrations for all of our equipment. It helps keep costs in check, and it also helps keep our product consistent and at the appropriate performance and quality. Okay, what was I getting at? Okay, so this is just a, we saw this slide earlier, but we use this for calculating the yield, and this is just another example of showing how if we're batching, we add up all these volumes here in the right column. When we add everything up, we are batching for 27 cubic feet of concrete, which is 1 cubic yard, and this is just an example and an approximation. Okay, so one slide that I do believe you guys have that I accidentally deleted and was not able to find because I am not good with computers. There's this nifty little chart thing that shows the three keys to curing something effectively. It shows time, temperature, and moisture. So with proper curing, your strength is going to increase, your concrete will be less permeable, so it's less susceptible to, you know, chloride attack or something like that. The concrete will be more durable, more resistant against abrasion. So if you pay attention to the time, the amount of time your concrete is curing, and you're applying like accelerated curing techniques or something like that at the appropriate times, that'll help. That's one of the keys to curing your concrete effectively. Additionally, temperature. So like we talked about earlier, we don't want our fresh concrete at the time of placing, we don't want it to be below 45 degrees, and we don't want it to be greater than 90 degrees, because that's going to affect our hydration reaction and how the concrete matrix, the crystals form and the matrix develops, and how dense and strong it's going to be. So time and temperature, and lastly is moisture. So someone asked earlier about moist curing procedures and whether or not that affects your water to cement ratio. It does not affect your water to cement ratio. When you, for example, if you are you're sprinkling the concrete, keeping it moist while it's curing, the water on the surface of your concrete is going to evaporate. And when you add a little bit extra water while it's curing, that just keeps things moist. It prevents plastic shrinkage cracking, and it keeps the concrete at an ideal moisture to make sure that all the cement is hydrating, and that cracks aren't forming because tensile stresses aren't forming because there's enough water to hydrate everything. So onto the slide that we're on now, advantages to heat. You can cure things a little bit faster. You can handle the product a little bit earlier, hopefully without breaking, as long as you're not throwing things around, and good luck throwing them because they're really heavy. But you get what I mean. Disadvantages to heat. Too much heat could potentially lead to lower ultimate strength if the reactions occur too quickly and the cement all doesn't get a chance to hydrate. And Claude, there's one more question. Can you read it, please?
So somebody asked a question, you said time was important for curing. How much time is required? We get that question all the time. So in cases like that, because we do go out and we talk to specifiers and regulators, and they say, yeah, we'll get somebody's product, and it hasn't cured for 28 days, so we don't know if we should accept it or not. And some of you are chuckling at that statement, but it's people do think that it takes 28 days for concrete to cure because of the 28-day strength that's attached to it. So we have to explain to them, and that's what your jobs are out there, is to educate your customers and say, well, actually, the 28-day strength is a specification. It says that it shall not take longer than 28 days to reach this strength. We can reach that strength in 24 hours, or we can reach that strength in 48 hours. So we're not baking cakes, to get back to Kayla's reference. We're making concrete. The nice thing about concrete is we can accelerate the cure. So every concrete's not the same. We use special admixtures. We do this, we do that, and we can achieve our 28-day strength in so much time, and we do not ship our products before they've achieved certain strength. So that's the answer to the question. People always want exact amount of hours or days. There isn't an exact number. It's the strength. As long as it's reached the strength, then it should be adequate for use, whether it's taken 1 day or 28 days.
Okay, thank you, Claude. Okay, so as you were saying, heat speeds up the hydration process. Sometimes you'll see, or how many of you guys use these heaters and tarp your products to keep the moisture in, keep the temperature at the appropriate height or at the appropriate level when you're curing? Does anybody use anything like this? One person said yes? Okay. So another, again, active curing is extremely important. You could have the most perfect mix design on paper, but if you just chuck it out outside in the sun and the wind and try to let it cure that way, it's just going to be a disaster and you're going to ruin it. So curing is extremely important. Every step of the process is. And in addition, all of the cement will never completely hydrate. But you can, the way you cure can maximize the effectiveness of your cement, one of the most expensive components of your concrete. And an example that I always hear Claude use is the Hoover Dam. There's still cement in the Hoover Dam that's still hydrating. So the next two slides are just some notable quotes that I found. So in order to obtain good concrete, the placing of an appropriate mix must be followed by curing in a suitable environment during the early stages of hardening. So again, your mix design itself is important, but what you do with it after you place it is also very important. It can very negatively or very positively affect the ultimate strength of your product. So additionally, moist curing is mentioned here. So you'd like to keep it moist and provide enough water for the cement to hydrate as the water does evaporate. Because, I mean, when concrete doesn't dry out, it's curing. The cement is hydrating. The water in your mix is not drying out necessarily. It is being consumed by that hydration reaction. It's not just all evaporating. Now, some of the water at the surface will evaporate, and if it evaporates at too quickly of a rate, then that can result in plastic shrinkage cracking, which we talked about earlier. So, as you can see here in this picture, you can use moist curing methods to try to mitigate some of those issues. So another cool graph that I thought would help explain this is, so this shows the compressive strength. Again, this is in megapascals, sorry, but, oh, over here, sorry. Okay. There's PSI on the right. But, so this gold line in laboratory air the entire time, so no moist curing, you can get, for this particular mix, about 4,000 PSI. But if you're using moist curing methods the entire time, you can almost double the compressive strength of your specimen, because you're enabling more of the concrete or more of the cement in the concrete to hydrate, and that's adding to its compressive strength. So if you don't use moist curing methods, you're not going to get a bad product, but you're leaving some of that cement in there unhydrated. There's no more water left to react with that cement. So all that expensive cement is just sitting in there with no water to hydrate it. It's not contributing to your compressive strength. It's just sitting in there. Okay, so if moisture is lost at too great a speed, it can lead to these plastic shrinkage cracks that we talked about earlier, the spidery, jagged-looking cracks. It can also lead to, it stunts the strength development. It can result in increased permeability and reduced abrasion resistance, all kinds of nasty things. So there are a lot of methods that you can use to prevent or reduce the amount of moisture that's lost. So you can tarp it or fog or all kinds of interesting things. Or sealant. Okay. There you go. Okay, so our last section is one of the coolest, I think, is the properties of hardened concrete. Okay, so the main studies that we're going to touch on are strength, durability, and volume stability. How cool is that? Look at that center or picture on the left. That's concrete. Whoever knew that could happen? So cool. Anyway, so strength. The definition is that it's a measure of the concrete's ability or resistance to the loads, the service loads that are applied to it. And concrete strength comes in three forms. It's compressive strength, tensile strength, and flexural strength. So first off, compressive strength, for just a typical regular old wet cast mix, it generally ranges from 3,000 to 6,000 psi. Now that depends on what the product is going to be used for, stuff like that. But typically it's between 3,000 and 6,000 psi. Compression is when you're, well, compressing, you're pushing it together. Concrete is very, very strong in compression. Tension, on the other hand, concrete is very weak in tension, so when you're pulling it apart, it only has about 1/10 of its compressive strength. So if your concrete has a compressive strength of 6,000 psi, in tension, if you're pulling it apart, it can only withstand approximately 600 psi. So it's extremely weak in tension. Now, flexural strength, so if you have it, if it's on two supports like this bottom picture down here, so we just showed what compression was right here, and then tension, pulling it apart. So flexure is when it's supported in two locations, it's being pushed down, so this bottom part is in tension and this top part is in compression. So it's kind of a combination of the two. And again, flexural strength doesn't even compare to the compressive strength. It's only 10 to 20% of that compressive strength. So one of the ways we get around this is to add reinforcement. So steel reinforcement, okay, so tensile strength of, let's say tensile strength of a 6,000 psi mix is only about 600 psi. So concrete tensile strength, let's say 600 psi. Tell me what the tensile strength of a typical grade 60 piece of rebar is. Brownie points if you get it right. That's worth a lot. What does that say? Anyone? Anyone? We have one response. Okay, well, typical grade 60 steel can have a tensile strength of 90,000 psi. So when you compare that to 600 psi that concrete has, you can see why when we combine them together we get such a great result. So when you use rebar or something like this, okay, let me erase. Oops. Oops. Oh boy. There we go. Okay. So when we have when we need to improve the tensile performance of the concrete, we'll put the rebar down here where the concrete will experience the greatest amount of tension. So the rebar will go down here and help increase the tensile strength of your specimen. So again, this little diagram just shows a beam in flexure. So it's the top part of it is in compression. All those little fibers are being squished together, and the bottom part of that beam is in tension. It's kind of stretching out in response to that force being applied. So engineering design is typically based on compressive strength, and a lot of other properties are are related to that compressive strength. So another property that we talked about is durability. So this is a case where you would want to use maybe type 5 cement, where it's going to be exposed to really harsh, extreme environments like salt water or whatever kind of nasty things are being transported in these pipes that are eroding the concrete. So when concrete is designed appropriately and cured appropriately, it can be very resistant to chemical attack or abrasion or sulfates or weathering, stuff like that. Additionally, volume stability. So we talked about how when concrete is exposed to freeze-thaw cycles, the water in the concrete will expand when it freezes, and that can, if it's not designed or if that's not taken into consideration when the mix design is made, it can have really negative effects and cause an increase in volume that the hardened concrete can't compensate for, so it results in cracking. So concrete has a tendency to change volume over time due to its ambient temperature and moisture surrounding it. But and combined with those volume changes, restraint like rebar can also result in cracks and impair the durability. I don't feel like that's as big of an issue, though. So, Claude, do you have anything to add about that? About volume changes combined with restraint can result in cracks and impair the durability of concrete. So, if, like for example, the coefficient of thermal expansion is kind of going into a PQS class, but concrete materials will expand and contract when they're exposed to different temperatures. And they all expand and contract at different rates. They all have different coefficients of thermal expansion. So when one is expanding very quickly and the other is changing very slowly, that imparts stress within the concrete, and that can also result in cracks. So when you have restraint, in this case, restraint is we're referring to rebar in your concrete. So steel and concrete will change volume at different rates when they are different temperatures. So that can sometimes have some negative effects on your concrete and result in cracking.
Right, yeah, reinforcing fibers, if they don't have a similar coefficient of thermal expansion, can be an issue, but usually it's not that type of restraint. It's restraint in the sense where you have, like, let's say you pour a slab on your floor, your plant floor, and you just pour it against the floor, you know, or you have some sort of bond breaker, obviously, but when that slab tries to shrink, which it tends to do when it hydrates, when it cures, the friction between the slab and the floor, that comes into play. That's a form of restraint. So if it's not, you know, if it's not an adequate bond breaker that enables that concrete to move slightly, then you might get some cracking there due to restraint. That's due to restraint against an outside body as opposed to reinforcing or aggregate. So.
Thank you, Claude. Okay, any questions on what we have discussed so far? Well, not so far. This is about time for a wrap-up. So, again, these slides weren't included. We can, Kathy, can we email the presentation that we're going through today? Can we email that out? Of course. Okay, so I just took, oops. Oh, and again, just another little tidbit. Heat, you know, the heat generated during the hydration reaction, that can cause expansion and contraction. Initial thermal changes begin when the water and cement are mixed because that hydration reaction is exothermic. So all of that stuff needs to be taken into consideration, but typically doesn't become a very large issue. So in summary, I just grabbed a couple slides from throughout the presentation. So we talked about the 5 basic types of concrete that we'll run into most often: wet cast, self-consolidating concrete, dry cast, and high performance or ultra high performance concrete. Fresh concrete is considered plastic, which means it's workable. We talked about the quantitative characteristics that we can give numerical values to. We also talked about the qualitative characteristics and other things that we can observe in the fresh concrete, like segregation and bleeding. We discussed the main basic constituent materials. Concrete is composed of water, cement, and aggregates. And then we went a little bit further into details regarding admixtures, air, and supplementary cementitious materials, or SCMs. Increasing your amount of water can lead to a reduced strength, and decreasing your amount of water can result in increased strength. The different types of cement, type 1 through 5 are most common, but type 1 is normal, general purpose that we see most often. And then we discussed the hydration process and the development of the concrete matrix and the densification, solidification of that matrix. We discussed the importance of admixtures and how they can affect our fresh and hardened concrete. We touched a little bit on the reinforcement, and then the properties of hardened concrete. So any questions that you guys have right now? If not, you can always just email us and we can get back to you. But if there are any questions, please let me know. Otherwise,
Okay. Thank you, Kayla. And thank you, everyone. We appreciate you taking the time to attend this presentation today. Your opinion counts in everything we do, and we appreciate your feedback. We will be sending out a link for viewing the playback of today's webinar, along with a link to a brief evaluation for you to complete. We'll also include as an attachment the updated presentation. If there are no further questions, this concludes today's webinar. Thank you for participating.